Welcome to the Depth Dive. Today, we're taking what I think is a necessary detour. We're going to step away from the big headline-grabbing concepts of Industry 4.0 for a moment.
Right, the things everyone talks about, the AI, the cloud computing, all the really complex robotic.
Exactly. We're going to dive straight into the actual engine room. We're focusing on the unsung heroes of manufacturing autonomy, that specialized, often overlooked hardware that, truly makes a smart factory run.
And we've got a fascinating stack of sources here. They all detail how manufacturers are trying to move beyond just simple automation.
Right.
They're racing toward full, seamless autonomy. And like you said, this transition isn't just a software upgrade. It really requires a radical shift in how the equipment itself interacts with its environment.
Exactly. So our mission for this deep dive is to unpack the mechanism that allows these factory systems to effectively feel their work, and crucially, to correct their own actions instantly. We're looking at how these tiny specialized sensors are creating genuinely autonomous production environments.
And the sources are, they're pretty unanimous on this. Modern manufacturing facilities rely on connected, automated systems. And the one underlying technology that ensures verifiable precision and control is force measurement.
Force measurement.
Specifically, advanced load cells. This technology is, and the sources call it this, the essential building block. Understanding its role is, I think, a true shortcut to being well-informed about I4.0 implementation.
Okay, that's a pretty strong claim, that force measurement is the central pillar here. So we need to move beyond thinking of these sensors as, just simple tools for general automation.
Like a weigh scale or something.
Right, exactly. We need to define what makes them I4.0 ready.
It really comes down to two things: connectivity and speed. A traditional load cell, it might measure weight for inventory, or maybe a batch check, perhaps once a minute.
Okay.
An advanced load cell, the kind that's essential for autonomy, it has to be a high-resolution digital sensor. It has to be capable of sampling thousands, maybe even tens of thousands of times per second. And that speed allows for instant sub-millisecond reaction times, which is what you need for real-time control.
So the key isn't just the measurement capability itself, it's the speed and the digital integration. That's what allows that measurement to become an immediate, actionable input for a larger system.
Precisely. If we look at the foundation of automation, the crucial question is this: what allows equipment to do more than just follow program's instructions?
It needs to be able to sense the process, right?
Yeah.
And self-correct.
Exactly. It needs to sense and self-correct.
Okay, let's explore that synergy. We know these high-speed load cells measure force, but what specifically makes them so crucial in this Industry 4.0 context? Why is this suddenly enabling autonomy where older versions of force measurement just couldn't?
Well, the breakthrough, and it really is a breakthrough, comes from pairing these advanced load cells with actuators.
With actuators, right? So the component that actually does the moving or the pressing.
That's it. An actuator is what applies the physical force. It might be a robotic gripper, a pneumatic press, or, a motor. Traditionally, the application of that force and the measurement of its result were two totally separate open-loop systems.
Okay, so you would program the actuator to press with, say, X amount of force. And then later on, a separate quality control check would verify the result. Maybe with a human operator or a different machine, there was a time delay.
Exactly. And that delay is the enemy of I4.0 efficiency. The new paradigm is this unified input-output system where the measurement is inherently linked to the action. The load cell measures the force as it's being applied or immediately after, and the actuator instantly adjusts based on that reading.
Oh, okay. So instead of a pre-programmed press and then a later check, the machine applies force, verifies resulting force in real time, and then adjusts the application mid-cycle.
That is the core technical concept. And this results in equipment that can both apply force and measure it automatically, all within the same operational cycle. This pairing creates what the sources call closed-loop test systems.
Closed loop.
Right. They don't just measure a variable. They measure, analyze, and adjust the output all within that same cycle. And they run with minimal, if any, human intervention.
If we contrast that with a legacy open-loop system, which was essentially prescriptive, right? It was do A, then later check the result B. The closed loop is more descriptive and adaptive. It's do A, monitor result B, and if B deviates from the ideal, instantly adjust A.
And this shift, it changes everything from a maintenance perspective.
Yeah.
You move from predictive maintenance, which is basically trying to guess when a machine will fail.
Which is better than nothing, but it's still a guess.
It's still a guess. Now you move to prescriptive, Real-time control, which ensures that optimal performance is maintained in every single instance. The system's output is always verified and corrected.
That is a powerful transition. Let's make this concept more concrete. Let's look at where this high-speed minimal oversight system is being deployed today. The sources gave an excellent and I think very relatable example from consumer electronics.
Yes, mobile device manufacturing. It's an industry that's just defined by incredibly high volume and absolutely zero tolerance for defects, particularly when it comes to user interface functionality. I mean, just think about the testing requirements for a modern touchscreen.
Right, we just take it for granted that every touch, every tap, every swipe is registered precisely. But when you're producing millions of units, how do they verify that every single one meets those sensitivity standards without just killing the manufacturing speed?
And this is where those miniature, highly specialized load cells come into play. They're using hardware like miniature load buttons. The sources specifically mention examples in the Convex BT product family. They're tiny, they're incredibly robust, and they have that necessary high-speed digital output we were talking about.
I can almost picture them, these little precise sensors integrated directly into the assembly apparatus itself. So how does the closed-loop system use them specifically for touchscreens?
So the mechanism combines these miniature sensors with high-precision linear actuators. The whole system is calibrated to test touchscreen pressure sensitivity at an incredibly high speed. The actuator moves to physically press the screen, applying a very precise regulated force. And the miniature load button measures the exact force that was exerted versus the screen's digital response time.
So it's not just a simple pass-fail test, it's a quantitative measurement of the entire force curve required for activation, right?
Exactly, you get the whole picture. And because that load cell is communicating digitally and instantaneously with the actuator, the system can self-calibrate. It can adjust its pressing motion dynamically to make sure the test parameters are met perfectly.
Even if the device jig, say, shifts by a tiny fraction of a millimeter.
Even then. And the key result here is, well, it's massive. This system allows every single unit on the line to be verified at production speed. You achieve 100% quality verification coverage.
And that is the ultimate goal of I4.0 quality control, isn't it? Eliminating batch sampling risk entirely. But, okay, if you're verifying every product hundreds of times a minute with these high-resolution sensors, the amount of force data you're generating must be enormous. Doesn't this just shift the bottleneck from, manufacturing defects to data storage and analysis?
That is an excellent question and one the sources addressed directly. Because you're right, if you tried to send all that raw, high-frequency force data to a central cloud, yes, the bandwidth and storage requirements would overwhelm most factory systems.
So how do they manage that torrent of high-resolution data?
They use edge computing and intelligent filtering, which is enabled by the load cell's digital interface. The load cell itself, or maybe a nearby embedded processor, it only transmits the summarized meaningful results.
So just the Pascal certification, the peak force, any anomalies?
Exactly, just the important stuff, not the thousands of raw data points that were collected during that 1-second test cycle. And this ensures the line stays at high speed, while only the critical process data gets archived for any downstream analytics, which, directly addresses your point about bottlenecks.
That's where the smart part of the smart sensor comes in. It doesn't just measure, it filters and it pre-processes the information.
Precisely. And then the process uses that distilled data to inform, say, upstream material selection or assembly process adjustments. So you get continuous improvement, not just intermittent improvement.
Okay, we've covered quality testing and verification, which is typically a static measure. You're testing a finished component. But the sources highlight another equally critical application. So let's shift to real-time process management. I find this application especially compelling because it moves from validating quality to actually guaranteeing process integrity.
Yes, this is where force measurement becomes a fully active feedback loop. It's about maintaining stability and accuracy during a dynamic assembly. It's the system's ability to prevent a defect before it can even form.
So how does a load cell, maybe when integrated into a robotic arm or beneath a moving track, how does it trigger a corrective action during a high-speed assembly task?
It works by defining force thresholds that signal an anomaly. Strategically placed force sensors are embedded directly into the structural components, so in robotic end effectors or beneath precision mounting plates or integrated into handling jigs. They're there to detect these minute, unplanned movements or pressure changes.
Can you give us an example of a dynamic process where this kind of self-correction is vital?
Sure. Let's consider high-precision material handling, maybe in fields like aerospace or medical device manufacturing, where components are incredibly delicate or highly valuable.
Okay.
Imagine a robotic arm picking up a complex composite component. If the vacuum gripper applies too much force, it could actually damage the component's structural integrity.
But if it applies too little,
The part might slip.
and a human operator just can't see the small internal stresses being caused by that gripper.
Correct. They can't see it. But the load cell, embedded right in the gripper, provides instant feedback. That sensor detects the exact force being exerted. And if the load shifts even slightly during movement, or if the initial gripping force exceeded a safe threshold, that's the anomaly, that data acts as an instant trigger.
And the corrective action is immediate. There's no human input needed at all.
None. The load cell identifies the unwanted pressure change, and it triggers the actuator, in this case the motor controlling the gripper, to instantly adjust its pressure. It either stabilizes the component or it relaxes the grip just enough to prevent damage.
So the system literally stabilizes itself. The source material mentions some specific immediate responses.
They did. They outlined several key real-time actions. Beyond just adjusting gripper pressure, the force data can trigger actuators to adjust conveyors, maybe to realign products that are sagging a bit. Or it can correct product positioning if a component is slightly off-kilter during insertion. Or, and this is critical, it can manage shifting loads to maintain stability during high-speed transfers.
This means the production line transforms. It goes from being a passive track that just waits for human intervention or one that relies on perfect components coming in,
Right.
into an actively managed ecosystem that self-regulates its own physical interactions.
It truly reinforces that idea of a fully autonomous system. The sensor provides the sense of touch the system needs to maintain its own health and integrity. This ensures that a consistent flow and high precision are maintained throughout the entire assembly process.
And that must drastically reduce scrap material and unscheduled downtime.
Two of the biggest efficiency killers in modern manufacturing. Absolutely.
This self-correction capability, it fundamentally changes the complexity of the operation. It moves the human role entirely toward high-level system optimization, rather than just minute process monitoring.
Absolutely. The value proposition is no longer about monitoring a machine. It's about relying on the machine to continuously optimize its own physical performance parameters.
Okay, so pulling back now, let's synthesize the big picture here. We've defined the technology, we've explored these closed-loop applications in quality testing and real-time correction. What does this load cell actuator interaction truly mean for the ultimate goal of Industry 4.0 efficiency?
I mean, at the end of the day, it means that the concept of digital intelligence finally translates into physical action. This seamless instant interaction between high-speed force sensors and automation hardware is what truly drives I4.0 efficiency. It's what bridges the gap between the digital command and the physical result.
So rather than being some hopeful future state, the adoption of these closed-loop force measurement systems is the definitive, implementable shortcut for manufacturers looking to achieve autonomy today.
That is the key takeaway. The sources, they distill the benefits down to three core advantages that are immediately recognized on the factory floor. First, it significantly reduces labor burden. By automating 100% verification and mid-process correction, human staff are freed from those repetitive, low-value monitoring tasks.
Which allows skilled technicians to focus on higher-value system maintenance and, innovation.
Correct. Second, it dramatically increases precision. Automated, calibrated force measurement eliminates the variability of human judgment, of fatigue. It ensures every action meets exact specifications.
Every time.
Every single time. And third, and this is the most crucial part, this technology enables fully autonomous processes. It delivers the kind of speed and consistency that manual or even older automated systems simply cannot match. This is the real difference between a high-tech factory and a genuinely self-managing factory.
The insight here is really clear. True factory autonomy isn't powered by the biggest machines, but by the precise, connected measurement tools that allow systems to feel, to react, and to verify their own output instantly. It's the sense of touch that enables the machine to think. Thank you for guiding us through these really fundamental sources today.
My pleasure. This transition to closed-loop force management is happening very quickly, and it raises an important question, I think, about the human element in this increasingly autonomous environment. If minimizing human intervention is the ultimate goal of the closed-loop system, what happens to the underlying intuitive human knowledge base of force application and measurement expertise? when the machine is always optimizing itself. That, to me, is the fascinating long-term implication to consider, the transfer of that specialized physical knowledge in these fully autonomous environments.